Our cosmic rulebook for the universe is fundamentally flawed. 25 paradoxical features in nearby galaxies are breaking our established models of reality, forcing a complete rewrite of astrophysics. By the end of this exploration, you will understand the specific cracks appearing in our understanding of dark matter, gravity, and galaxy formation itself. How can entire galaxies exist without the invisible dark matter thought to bind them together? Why do the smallest galaxies spin in ways that defy every prediction? What does all this mean for our most basic laws of physics? The answers are hidden in plain sight within our galactic backyard. Are you ready to see the universe in a completely new way? Our cosmic simulations paint a picture of a bustling galactic neighborhood, one teeming with hundreds of small dwarf galaxies orbiting giants like our own Milky Way. Yet when we look up, the reality is startlingly quiet. We find only a handful of these tiny companions. This glaring mismatch between prediction and observation is the first great paradox, known as the missing satellite problem. It strikes directly at the heart of our most successful model of the universe, lambda cold dark matter. The model works beautifully on the grandest scales, but here, in our own backyard, it seems to break down. It tells us that the dark matter halo surrounding our galaxy should be filled with countless small clumps of dark matter, each a potential cradle for a tiny galaxy. Our telescopes, however, see empty cradles. It is as if we predicted a crowded party but arrived to find only a few scattered guests, leading scientists like Dr. James Bullock have pointed to this quiet cosmic frontier as one of the most persistent puzzles in modern cosmology. So where did all the missing galaxies go? Perhaps star formation in these small dark matter halos is incredibly inefficient, preventing them from lighting up in a way we can see. Another possibility is that the intense ultraviolet radiation from the universe's first stars, an era called reionization, may have stripped away the gas needed for these fledgling galaxies to ever form stars, leaving them dark and invisible. But these explanations are incomplete, like placing a single piece into a vast, unsolved puzzle. The silence from our galactic halo is a profound clue, whispering that something fundamental is missing from our equations. And this initial crack in our model is just the beginning, leading us directly to a second, even stranger dark matter mystery. The very center of a galaxy should be the most telling place to find dark matter's signature. Our most trusted simulations paint a consistent picture, a dense, sharply peaked concentration of this invisible substance at the galactic heart, a feature astronomers call a cusp. It is a logical prediction, the inevitable result of gravity pulling matter inward. Yet when we observe the actual rotation of stars and gas in many dwarf and low surface brightness galaxies, the story changes entirely. Instead of that expected spike, we find a soft, gentle distribution, a constant density core. This glaring mismatch is the cusp core problem, and it strikes at the very nature of dark matter itself. How can our predictions be so definitively wrong about something so fundamental? The answer may lie not with dark matter alone, but with the turbulent lives of stars. Astrophysicist Dr. Elena Donghia points to a process known as baryonic feedback. Imagine the powerful stellar winds from massive stars and the cataclysmic energy of supernova explosions. These are not gentle forces. They can churn the central regions of a galaxy, generating waves of energy that push and pull on the surrounding material. This constant stellar activity might be acting like a cosmic mixer, effectively stirring the dark matter and scattering it outward, gradually eroding the sharp cusp into a flattened core. It is a compelling idea that the very visible matter we understand could be sculpting the invisible matter we do not. This paradox forces a difficult choice. Either dark matter is not the simple, non-interacting particle we have long assumed, and it possesses some unknown way to interact with itself, or our models have profoundly underestimated the power of ordinary matter to reshape its dark environment. Both possibilities lead us to a startling conclusion that the centers of galaxies are not the quiet, predictable places we imagined, but arenas of a complex and ongoing tug of war between light and shadow. And just as we question the heart of a galaxy, we must also confront the unexpected ways in which these vast islands of stars move through space. But what if a galaxy's entire history is written not in its violent encounters, but in its quiet, undisturbed growth? Our third paradox focuses on the elegant simplicity of the spiral galaxy. The standard story of galaxy formation is a dramatic one, filled with colossal collisions and major mergers. These cosmic crashes, according to our most advanced simulations, should be the primary architects of galactic structure. They fling stars into chaotic orbits, puffing up the central region to create a distinct, bright bulge, a feature thought to be as fundamental to a mature spiral as the rings of a tree. Yet when we look at countless spiral galaxies, we find something profoundly different. Many of them, like the beautifully flocculent NGC 300, are pure, pristine disks with no central bulge at all. This is the bulgeless disk galaxy paradox. It is as if we discovered a vast, ancient forest where half the trees had no rings, suggesting they grew without any of the seasonal hardships we assumed were universal. Astronomers like Dr. Bruce Elmergreen propose a far gentler narrative for these galaxies. Instead of a violent upbringing defined by mergers, they may have formed slowly and quietly through the steady, continuous accretion of cold gas from intergalactic space. Imagine a delicate snowfall gradually building a smooth, unbroken layer, rather than a series of avalanches creating a jagged, tumultuous landscape. This gentle process allows a thin, orderly disk of stars to form and persist for billions of years, completely avoiding the disruptive violence that forges a central bulge. High-resolution surveys of the local universe now reveal that these thin, bulgeless disks are not rare anomalies, they are incredibly common. Our existing simulations struggle to create them without meticulous, almost artificial, fine-tuning of the parameters. This widespread absence of bulges tells a compelling new story about galactic history. It suggests that for many galaxies, life can be a long, peaceful journey of steady accumulation, a far cry from the violent, collision-dominated past we once imagined. So, if a galaxy can live a life of such serene stability, what happens when we find one that seems impossibly young, a vibrant teenager in a universe of elders? Some galaxies hold a secret of eternal youth, a paradox written in the light of their stars. We expect the vast disks of spiral galaxies to be ancient structures, having settled into their orderly rotations billions of years ago and aged uniformly ever since. Yet when we look at a galaxy like UGC 7321, we see something that defies this aging process. Its stellar disk is remarkably thin, dominated by young blue stars, and shows a very low velocity dispersion, meaning its stars are moving on incredibly calm, orderly orbits. It looks like a galaxy in the prime of its life, yet it is likely very old. This is the paradox of the unexpectedly young stellar disk. How can a structure so fragile and pristine survive for so long in a universe we thought was dominated by chaos? Astronomer Dr. Roloff de Jong notes that such a delicate galaxy could only exist if it has lived an exceptionally quiet and sheltered life. one continuously fed by a steady inflow of cold gas to fuel new star formation while avoiding any major disturbances. Our best cosmological simulations, however, paint a much more violent picture of a typical galaxy's life. They are filled with frequent minor mergers, accretion events, and close encounters with neighboring galaxies, all of which stir up a disk, thickening it and making its stellar orbits more random and turbulent. The serene existence of UGC 7321 suggests that some galaxies are cosmic recluses, managing to avoid the frantic social life of the cosmos for eons. This forces a profound question about galactic evolution. Is the violent, merger-heavy pathway we simulate truly the norm, or is there a far more peaceful road to maturity that we have largely overlooked? The survival of these youthful disks tells us that a calm, gas-rich history is not just a possibility, but a reality for many galaxies, a reality our models struggle to recreate. This puzzle of a tranquil life naturally leads us to another, the strange case of galaxies that are not just calm, but profoundly and inexplicably alone. A tiny, isolated galaxy should be a quiet, fading ember in the vast cosmic dark, far from the gravitational influence of any larger galaxy, with no neighbors to stir it into action. Its star-forming fires were expected to sputter and die. Yet the dwarf galaxy Leo P tells a different story. It floats in profound solitude, a single speck of light in an immense void, and against all expectations, it is alive with the brilliant blue glow of newborn stars. This is the paradox of isolated dwarf galaxy star formation, a phenomenon that shatters the idea that a galaxy needs company to thrive. How can such a small, lonely galaxy muster the energy for a stellar baby boom? Astrophysicist Dr. Kristen McQuinn points to an internal lifeline, a subtle and continuous trickle of cold gas flowing in from the cosmic web. This pristine fuel, cooler and denser than the hot gas typically found in galactic halos, can directly feed the galaxy's star-forming reservoirs. Our standard models, however, often struggle to account for this process in such low-mass systems. They tend to underestimate how efficiently this gas can cool and collapse to form stars, predicting a passive, fading existence that simply does not match the vibrant reality of objects like Leo P. These active, isolated dwarfs are a powerful testament to self-reliance, proving that a galaxy's internal engine, its ability to draw fuel from the cosmos and convert it into starlight, can drive its own evolution completely independent of its environment. They are cosmic hermits, not just surviving but flourishing on their own terms. This defiance of a quiet fate forces us to reconsider what truly ignites a galaxy's potential. And if a small galaxy's vigor can come from within, what does that imply about the invisible dark matter scaffolding that supposedly supports it, especially when that scaffolding itself appears to be missing? Our most powerful cosmological simulations create a universe that is almost too perfect, filled with a hierarchy of dark matter halos of every size. Some of these predicted structures are true behemoths, the most massive subhalos orbiting galaxies like our own. They possess such immense gravitational pull, such deep potential wells, that they should be absolutely brimming with stars, forming brilliant satellite galaxies that dominate our night sky. This is the too big to fail problem, a paradox where the universe's most capable builders are failing at their one job. In our simulated reality, these colossal halos are bustling metropolises. In our observed reality, they are ghost towns appearing far too dim and star-poor for their immense underlying mass. Astronomer Dr. Marla Jeha and her team have meticulously measured the real satellites of the Milky Way, finding them to be significantly less massive and luminous than their simulated counterparts should be. It is as if we calculated the perfect foundation for a skyscraper, only to arrive and find a modest cottage built upon it. Why do these mighty halos consistently underperform? The answer may lie in the very nature of star formation within them. One compelling idea points to the ferocious power of stellar feedback. In these relatively small but massive halos, the first waves of star formation could have been catastrophically intense. Supernova explosions from these early, massive stars might have generated tremendous galactic winds, powerful enough to overcome the halo's gravity and violently eject nearly all of its remaining star-forming gas into intergalactic space. The galaxy, in essence, strangled its own future in a frenzied burst of youthful activity. Another, more radical possibility is that our assumptions about dark matter itself are incorrect. Perhaps dark matter particles are warmer or can interact with each other in ways that suppress the formation of such extremely dense subhalos. Both explanations point to a universe where galaxy formation is a far more delicate and inefficient process than we ever guessed, especially in these specific environments. The most promising construction sites in the cosmos are ending up vacant, and this failure forces us to question the fundamental relationship between a dark matter halo and the luminous galaxy it is meant to host. If the most massive halos can remain dark and quiet, what does that imply for the very rules that govern how all galaxies spin? The graceful spin of a dwarf galaxy holds a secret our physics struggles to explain. Picture a distant star tracing a slow, steady orbit far from the galaxy's bright center. According to Newton's laws, its speed should fall away the farther it travels, just as the outer planets in our solar system move more sluggishly than those close to the Sun. Yet in countless dwarfs like IC 2574, this is not what we see. The rotation curve remains stubbornly, impossibly flat. Stars and gas clouds at the very outskirts race along at virtually the same speed as those near the core. This flat rotation curve is the classic signature of dark matter, an invisible halo whose gravity grips the entire galaxy. But the precise shape and extent of this curve in small galaxies creates a deeper puzzle. It reveals a strangely perfect correspondence between the distribution of the visible stars and gas and the strength of the gravitational field itself. This detailed match is not what our standard dark matter models perfectly predict. Astrophysicist Dr. Stacy McGaw points out that this tight relationship is so exact that alternative theories, like modified Newtonian dynamics or MUND, can beautifully fit the rotation curves of many isolated dwarfs. MUND proposes that on very large galactic scales, gravity behaves differently than Newton described, eliminating the need for dark matter entirely. Yet this elegant solution faces its own profound failures in other contexts, like within galaxy clusters. So we are left with a deep anomaly. How does the visible matter in a dwarf galaxy so precisely dictate the behavior of the dark matter halo surrounding it? It is as if the luminous tail is wagging the dark, invisible dog. This paradox suggests that either our understanding of dark matter's fundamental properties is incomplete, or our law of gravity itself requires a subtle but crucial revision on cosmic scales. The unwavering spin of these smallest galaxies is a silent, persistent challenge to the very rules we use to describe reality. And just as the motion of a galaxy as a whole can defy expectation, so too can the intricate structure hidden within its swirling arms. A galaxy is supposed to be anchored by its own shadow. The invisible dark matter halo is its true skeleton, its primary source of mass and gravitational might. But then we found galaxies like NGC 1052, DF2, objects that defy this foundational principle. They appear to be almost empty of dark matter, ghost ships sailing through space with scarcely any of the invisible glue we thought was essential for their very existence. This discovery is profoundly unsettling. It creates a paradox that cuts to the very core of our cosmological models. How can a galaxy hold itself together without the dominant presence of dark matter? Astronomer Dr. Pieter van Dokkum and his team have proposed a dramatic solution, a cosmic catastrophe. They suggest that a high-speed collision, a violent gravitational encounter between galaxies, could have torn the dark matter away from the stars. In this scenario, the diffuse dark matter halo, being much larger than the stellar component, is more easily stripped away by tidal forces, while the more compact collection of stars passes through the encounter relatively unscathed. It is a compelling story of cosmic theft, where a galaxy is robbed of its dark essence. Yet, such extreme interactions are thought to be exceptionally rare, and we are finding more of these dark matter-deficient galaxies than this explanation can comfortably account for. This forces a difficult line of questioning. Are our measurements of these galaxies' masses somehow flawed, perhaps misjudging the amount of ordinary matter present? Or, more fundamentally, does their very existence challenge the idea that dark matter is the indispensable scaffold for all galaxy formation? If a galaxy can indeed form and persist without this invisible foundation, we must reconsider what truly binds a galaxy together. The quiet defiance of NGC 1052, DF2 whispers that the relationship between dark matter and the stars we see is far more complex and fragile than we ever imagined. A galaxy can be a ghost of its former self, vast in scale yet almost empty of substance. These are the ultra-diffuse galaxies, cosmic mirages as large as the Milky Way but containing only 1% of its stars. They are so faint they nearly vanish against the blackness of space, their light stretched into a gauzy, ethereal web. The existence of these spectral giants, like the famous Dragonfly 44, presents a profound formation mystery. How can a galaxy acquire the mass of a giant yet fail so completely at the most basic task of making stars? Astronomer Dr. Roberto Abraham suggests two possible, almost tragic, life stories for these objects. One possibility is that they are failed galaxies, systems that gathered a tremendous reservoir of dark matter and gas early on, but for some reason had their star-forming fuel stripped away or heated up before they could truly begin. Another idea points to internal feedback, where early bursts of star formation generated such powerful winds that they pushed the galaxy's remaining gas outward, causing the entire system to permanently expand and puff up into its current diffuse state. Our most sophisticated simulations have a difficult time creating these faint giants in the numbers we actually see. To make them, modelers often have to invoke very specific and perhaps unlikely conditions, such as dark matter halos that are spinning at exceptionally high rates, which would naturally resist the collapse needed for efficient star formation. Alternatively, the gentle but persistent gravitational pull from a neighboring galaxy, a process called tidal stripping, might have slowly stretched an ordinary dwarf into a cosmic phantom. The sheer abundance of ultra-diffuse galaxies tells us that galaxy formation is not a single, straightforward path, but a tree of many divergent possibilities, including paths that lead to spectacular underachievement. Why some galaxies choose to spread their stars so thinly remains an open question, one that forces us to look not just at a galaxy's structure, but at the very elements that compose it. The chemical fingerprints within these stars reveal another layer of mystery, a paradox written in the language of cosmic metals. The chemical fingerprint of a galaxy is written in the light of its oldest stars, a permanent record of its fiery origins. Yet when we read this cosmic history in the smallest dwarf galaxies, we find a story that does not match our predictions. This is the alpha element abundance paradox. Elements like oxygen and magnesium, forged in the violent hearts of massive stars and scattered by their supernova deaths, should follow a very specific pattern as a galaxy ages. Our models tell a straightforward tale, a rapid, early burst of star formation, dominated by these short-lived giant stars, should leave the galaxy permanently enriched with a high ratio of these alpha elements to iron. But in many dwarf satellites, the story is far more muddled. The chemical abundances we measure are often too uniform, or they follow trends that our standard supernova yield calculations simply cannot reproduce. Astrophysicist Dr. Anna Frebel highlights the intricate factors at play. The universe is not so simple. Different types of supernova contribute their own unique chemical signatures, and a galaxy's star formation rate might not have been a single burst, but a stuttering stop-and-start process that constantly alters the chemical mix. For instance, some dwarf galaxies show a surprisingly consistent level of alpha enhancement across many stars, as if the products of countless supernovae were perfectly blended throughout the entire system. Our models, however, often predict pockets of unmixed gas, leading to much greater variation from star to star. This points to a more turbulent and efficient mixing process in these small galaxies than we ever anticipated. Alternatively, the initial mass function, the blueprint for how many stars of each size are born, might have been different in the early universe, producing a different balance of elemental factories. These subtle chemical discrepancies are more than just academic curiosities. They are direct evidence that the early lives of galaxies were far more complex and chaotic than our clean simulations can capture. The violent winds from supernova did not just enrich the gas, they must have churned it, heated it, and perhaps even expelled it entirely, shaping the chemical destiny of every star that would form afterward. What do these elemental fingerprints ultimately reveal? They tell us that the recipe for building a galaxy involves forces we are only beginning to comprehend, forces that not only forged the elements but also generated immense, invisible fields of power. This chemical mystery leads us directly to a paradox of galactic magnetism. The faintest galaxies in the cosmos are hiding a surprising source of power. A small, turbulent dwarf like IC10 should be a simple place, lacking the complex internal machinery of its larger cousins. Yet observations reveal it possesses a coherent, large-scale magnetic field, a phenomenon that should require the sustained dynamo action of a vast rotating disk. This is a profound paradox. How can a galaxy with such feeble gravity and slow spin generate and maintain an invisible force field spanning thousands of light years? Astronomer Dr. Rainer Beck points to possible origins in the galaxy's violent interior. The intense turbulence from supernova explosions and stellar winds might act as a small-scale dynamo, chaotically twisting and amplifying magnetic seed fields left over from the early universe. Alternatively, a past gravitational encounter with a neighboring galaxy could have stirred the dwarf's gas, stretching and organizing these magnetic lines into a larger, more ordered structure. Our standard models, however, struggle to replicate this. They often predict that dwarf galaxies should host only weak, disordered magnetism, incapable of cohering on such a grand scale. The reality we observe is different. The presence of these organized fields implies that the fundamental processes of magnetic amplification are astonishingly efficient, even in the most rudimentary galactic environments. This invisible architecture is not just a curiosity, it actively shapes the galaxy's destiny. These magnetic fields can influence the collapse of gas clouds, regulate the birth of new stars, and guide the flow of material throughout the dwarf. The fact that such a faint system can generate this kind of large-scale force suggests our understanding of cosmic magnetism is still in its infancy. If a simple dwarf can defy our expectations about magnetic fields, what other fundamental resources might these galaxies possess in surprising abundance? This leads us directly to a new puzzle, one concerning the very fuel that powers a galaxy's future. A galaxy can be brimming with potential yet remain frozen in time. The dwarf galaxy Leo T is a perfect example of this contradiction, a small, ancient system teeming with vast reservoirs of neutral hydrogen gas, the very raw material for creating stars. By all rights, this abundant fuel should have sparked a firestorm of stellar birth, lighting up the dwarf in a brilliant display. Yet Leo T has formed very few stars throughout its long history. It is a cosmic engine idling quietly, refusing to roar to life, and this presents the paradox of the gas-rich survivor. How can a galaxy hold onto so much fuel for so long without using it? Our standard models tell us that gas in such small, shallow potential wells should be easily consumed by star formation, or just as easily blown away by the first supernova that erupts. But in Leo T, the gas remains stubbornly stable and unevolved. Astronomer Dr. Jana Giarcevich explores two primary forces that could be acting as a cosmic preservative. The first is the pervasive fog of ultraviolet radiation that fills the universe, a relic from the first stars and galaxies. This cosmic UV background constantly bathes the gas in Leo T, gently heating it and preventing it from cooling down and collapsing into the dense clouds required to form stars. The second possibility is internal turbulence, where random motions within the gas itself provide enough pressure to support it against its own gravity, effectively putting the star formation process on permanent hold. Our most advanced simulations, however, consistently fail to replicate this delicate balance. They tend to overpredict star formation in these environments, turning gas-rich dwarfs into star-forming powerhouses that simply do not exist in our observations. This tells us we are missing crucial physics in our understanding of how gas cools, stabilizes, and resists collapse in the most pristine galactic environments. The enduring calm of Leo T is a silent lesson in galactic self-control, a demonstration that simply having the ingredients for creation is not enough. You need the right conditions to bring them together, a recipe we have yet to fully decipher. This puzzle of a galaxy holding its breath leads us directly to the next paradox, one written in the looping, unpredictable paths that galaxies take through the cosmos. The orderly dance of satellite galaxies presents a paradox of cosmic choreography. We expect these smaller companions to orbit their host in a random, spheroidal swarm, a natural result of them falling in from all directions over billions of years. Yet around our own Milky Way and around our neighboring galaxy Andromeda, we find something entirely different. The satellites are not scattered chaotically. They are aligned in a breathtakingly thin, rotating disk, a structure astronomers call a vast polar structure. It is as if you tossed a handful of marbles into the air only to watch them spontaneously arrange themselves into a perfect, spinning ring. This organized configuration is staggeringly unlikely within our standard cosmological simulations, which predict a much more disordered distribution. Astronomer Dr. Marcel Pawlowski has championed the idea that these planes are fossils of a dramatic past, the shredded remains of a single, larger galaxy that was torn apart by tidal forces during an ancient encounter. In this scenario, the satellites are not independent actors but siblings, born from the same event and thus sharing a common orbit. While this is a compelling story, our most comprehensive models of the universe struggle to reproduce the sheer thinness and coherence of these planes without invoking what feels like special, fine-tuned conditions. The persistence of these structures whispers a deeper secret, that the accretion of satellites may be a far more organized process than we thought, or that the invisible dark matter subhalos they inhabit have orbits that are somehow correlated from the very beginning of time. Why do these satellites prefer to dance in formation, defying the expected chaos of the cosmos? This question of galactic structure and the rules that govern it leads us to another profound mismatch, one that concerns the fundamental relationship between a galaxy's visible size and its invisible dark matter content. Ancient galaxies hold a secret of impossible density. In the distant, early universe, we find massive galaxies that are far more compact than any model predicted, defying the standard story of how galaxies grow. Our most trusted simulations tell a tale of gradual expansion, where galaxies slowly puff up over billions of years through a steady diet of minor mergers and the accretion of new material. But the light from these high redshift giants reveals a different history. They appear to have built nearly their entire stellar mass in a phenomenally dense, incredibly small core, and they did it with breathtaking speed. This is the size evolution tension, a paradox that questions the very engine of galactic growth. How could such massive structures assemble themselves into such a tiny, concentrated form so early in cosmic time? Astronomer Dr. Seun Toft's work highlights the core of the problem. The primary mechanism we rely on to explain galaxy growth, a series of dry mergers involving mostly stars and dark matter, seems insufficient to create the specific properties we observe in these ancient compact galaxies. If mergers were the dominant force, we would expect to see more evidence of disturbance, more signs of a chaotic assembly. Instead, we find these dense red nuggets, looking as if they formed in a single, rapid, and remarkably calm collapse. This suggests a far more efficient and direct path to maturity, one that bypasses the protracted merger process we once thought was universal. The answer may lie in the internal dynamics of the galaxy itself. Perhaps intense feedback from star formation or a central supermassive black hole acting within a gas-rich disk triggered a sudden, violent inward rush of material. This premature compaction could have funneled a galaxy's entire gas reservoir into its core in a short, furious burst of star formation, creating a dense stellar city long before the slower, merger-driven expansion could even begin. The details of this process, however, remain one of the great unsolved puzzles in galaxy evolution. How does a galaxy's own internal feedback, the very energy it generates, dictate its final size and shape? This mystery of ancient density forces us to look more closely at the powerful winds and outflows that a galaxy can generate. The very forces that give a galaxy life can also condemn it to a quiet existence. Our models rely on powerful feedback mechanisms, the cosmic exhaust from supernova explosions and active supermassive black holes, to regulate star formation and prevent galaxies from growing too large too fast. This stellar and active galactic nucleus feedback is meant to act as a careful thermostat, ejecting gas to keep the system in balance. Yet in many real galaxies, this thermostat seems to have been set to an extreme. The feedback is catastrophically over-efficient, blowing away nearly all of the star-forming fuel and permanently stunting the galaxy's growth. This is the paradox of over-efficient feedback, a situation where our simulations must invoke these powerful winds to match certain observations, but in doing so, they often create galaxies that are too faint or whose dark matter halos are too massive for their paltry number of stars. Leading astrophysicist Dr. Rachel Somerville points out that tuning the strength of these feedback processes remains one of the greatest uncertainties in our models. We see a wide spectrum of feedback impacts in nature. some galaxies show clear evidence of gentle, regulated outflows, while in many dwarfs, the feedback appears to have been a single, devastating event. Imagine a young galaxy experiencing its first wave of star formation. Instead of a manageable series of supernovae, it might have suffered a coordinated chain reaction of explosions. This could have generated a galactic superwind, a torrent of energy so violent it overcame the galaxy's own gravity, sweeping its entire reservoir of gas into intergalactic space in one irreversible exodus. The galaxy was left gasping for fuel, its potential for future growth extinguished almost as soon as it began. Why does this feedback switch sometimes flip to a destructive overdrive? The answer may lie in the delicate timing and environment of these early explosions. In a small, shallow gravitational potential, even a modest amount of stellar feedback can have runaway consequences, a fragility that our coarse simulations might still struggle to capture with perfect accuracy. This leaves us with a profound question about the recipe for a galaxy. How much turbulence is necessary for healthy regulation, and how much leads to irreversible starvation? The silent, faint galaxies we observe are the enduring legacy of feedback that worked far too well. This puzzle of missing starlight from overactive engines leads us to another, the mystery of galaxies whose light is not just faint, but distributed in a way that defies all expectation. The violent deaths of the universe's most massive stars create the very elements that make our world possible, but the rate of these cosmic collisions holds a deeper mystery. Our best models for how galaxies evolve and produce binary neutron star systems predict a certain rhythm for these mergers, a specific number of cosmic crashes per year. Yet the data from gravitational wave observatories like LIGO and Virgo tell a different story. The universe seems to be orchestrating these events at a pace our models cannot explain. This is the double neutron star merger rate discrepancy, a paradox that connects the intimate deaths of stars to the grand architecture of galaxies. Astrophysicist Dr. Vicky Calodra notes the intricate factors at play. The journey of two massive stars born together in a binary system is fraught with uncertainty. Their final fate depends on the chemical makeup of their birth cloud, with lower metallicity environments potentially forging more neutron stars and black holes. Their survival is also a matter of environment, as dynamical interactions within dense star clusters can either tear binaries apart or forcefully shove them together, dramatically accelerating their merger timeline. Our current galaxy models, it seems, may be underestimating the number of these tightly bound cosmic time bombs, or misjudging how quickly their orbits decay through gravitational radiation. The tension with the LIGO-Virgo data is a clear signal that our understanding of stellar life cycles is incomplete within the larger context of galaxy assembly. How do the violent, small-scale deaths of stars connect so directly to the large-scale structure and history of their host galaxy? The answer is written in the gravitational waves themselves, a cosmic drumbeat whose tempo we are only beginning to measure. This intricate link between stellar death and galactic life forces us to look at another fundamental component of a galaxy, the vast, cold reservoirs of gas that serve as the raw material for everything we see. The edge of a galaxy is not a hard boundary, but a fading of starlight into an unseen ocean of potential. While our telescopes capture the brilliant spiral of a galaxy like M83, they reveal only the inner island of its true domain. Far beyond this luminous coast, vast, invisible reservoirs of neutral hydrogen gas stretch into the darkness, forming a gargantuan disk that can be several times wider than the starry disk we see. This is the paradox of the extended hydrogen disk, and its very existence defies a fundamental expectation. In our models of an evolving universe, such immense, fragile structures of cold gas should not survive for long. They should be quickly stripped away by intergalactic winds, heated to invisibility by the cosmic ultraviolet background, or rapidly accreted inward to fuel star formation. Yet they persist, these silent, sprawling halos of hydrogen, as documented in the work of astronomers like Dr. D.J. Pisano. Their endurance tells us that our understanding of a galaxy's relationship with its environment is incomplete. These extended disks are not just celestial curiosities. They are the strategic fuel reserves for a galaxy's future, a deep well of raw material that will, over billions of years, slowly drain inward to birth new generations of stars. Their stability points to an unexpectedly calm and protective halo, a dark matter cradle that effectively shields this tenuous gas from the harsh conditions of intergalactic space. It also suggests that the gas is able to cool with remarkable efficiency, allowing it to remain neutral and detectable rather than heating up and dispersing. The origin of this immense gas supply remains a topic of intense debate. Did it slowly accumulate from the steady, cold accretion of filaments from the cosmic web? Or was it captured during a gentle, long-ago merger with a smaller, gas-rich companion? The quiet defiance of these extended disks forces a simple but profound question. How does a galaxy manage to hold onto its gaseous halo so effectively across cosmic time, preserving the very ingredient it needs for its own longevity? This mystery of a galaxy's hidden bulk naturally leads us to question the nature of the stellar populations that form from this fuel. A galaxy can be a cosmic phoenix, bursting into brilliant life long after its time should have passed. This is the paradox of the blue dwarf galaxy, a place like Zwicky 18, which glows with the fierce blue light of newborn stars despite an age that suggests it should be quiet and red. Our standard models of galactic evolution often paint a simple picture for these small systems. They form their stars early and quickly, then fade into a long, passive retirement as their gas is exhausted or stripped away. But the vibrant existence of blue compact dwarfs tells a far more dynamic story. These are not galaxies in decline, they are galaxies experiencing a dramatic rebirth. Astronomer Dr. Trinh Thuan has dedicated his career to understanding these stellar late bloomers. He points to a rhythm of episodic star formation, where immense bursts of stellar birth are separated by long periods of deep quiescence. How does a galaxy achieve this? The secret lies in a delicate cosmic fuel line. A sudden, external trigger, like a slow-motion collision with a neighboring cloud of primordial hydrogen, or the steady, internal accretion of gas from its own extended halo, can send a fresh wave of cold fuel rushing into the galaxy's core. This influx ignites a firestorm of star formation, painting the dwarf blue once again. Our most sophisticated computer simulations, however, consistently struggle to replicate the precise timing and ferocity of these bursts. They fail to capture the exact conditions that allow a galaxy to sleep for 1 billion years and then suddenly awaken in a blaze of glory. This mismatch suggests we are missing crucial physics in our understanding of how gas flows into these small systems and what exactly triggers its collapse. The enduring youthfulness of galaxies like Zwicky 18 forces a profound question about galactic life cycles. Is aging an inevitable one-way path, or can it be a series of cycles with dormant galaxies waiting for the right moment to be reignited? The answer challenges our most basic timelines and leads us directly to a new puzzle, one written in the fundamental relationships that supposedly govern every galaxy's structure. The relationship between a galaxy's mass and its spin is one of the most reliable rules in all of astronomy. Known as the Baryonic Tully-Fisher relation, It tells us that the total amount of ordinary or baryonic matter in a spiral galaxy, its stars and gas, is tightly linked to how fast it rotates. It is a beautifully simple and powerful correlation, a cornerstone of our understanding, but like so many rules in the cosmos, it has its exceptions. The 19th paradox lies in the subtle scatter of this data, the outliers that drift just beyond the neat line we have drawn. For some galaxies, the rotation speed is just a bit too fast or too slow for their apparent mass, creating a scatter larger than our models can easily accommodate. This scatter is not random noise, it is a whisper of hidden complexity. Astronomer Dr. Michel Capellari's work highlights what this scatter implies. It suggests that the efficiency of galaxy formation is not a uniform, one-size-fits-all process. Why would two galaxies with the same rotation speed end up with different total amounts of ordinary matter? The answer lies in the invisible dark matter halo itself and the galaxy's own violent history. A galaxy that has experienced more intense stellar feedback, with powerful supernova winds blowing its gas around, might have a different distribution of mass compared to a galaxy that has lived a calm life. A dramatic merger history could have stirred up and redistributed both its dark and visible matter in unique ways. Even the intrinsic concentration of the dark matter halo, how densely packed it is at the center, can vary from system to system, altering the final relationship between rotation and mass. These outliers, these galaxies that refuse to sit perfectly on the line, are telling us that the journey from a dark matter halo to a luminous galaxy is filled with countless subtle variations. They are cosmic individuals, each with a unique story of feedback, interaction, and accretion imprinted on its fundamental properties. The overall rule remains robust, a testament to the dominant role of dark matter gravity, but the scatter is the signature of a more intricate and personal history. This delicate link between a galaxy's spin and its mass leads us to wonder about the material it cannot hold onto, the powerful outflows that shape its very existence. A galaxy can breathe its own exhaust back to life. This is the paradox of galactic wind recycling, a cosmic cycle of death and rebirth that challenges our simulations. We have long understood that powerful winds, driven by supernova and stellar fury, blast gas out of a galaxy's disk. Our models assumed this expelled material was largely lost forever, vented into the vast emptiness of intergalactic space, a necessary sacrifice to prevent runaway star formation. Yet observations of starburst galaxies like NGC 253 reveal a different fate for this material. Immense fountains of hot gas are indeed launched outward, but instead of escaping entirely, a significant portion of this material rises, cools, and condenses into dense clouds that then rain back down onto the galactic disk. This returning rain is pristine fuel for future generations of stars, a process of reaccretion that our most detailed computer models struggle to replicate with the right efficiency. Astrophysicist Dr. Crystal Martin's research highlights the core of this tension. In simulations, the galactic winds are often either too weak, failing to eject enough metal-enriched gas, or too effective, blowing the material so far away it can never return. Getting the balance just right, the delicate choreography of the fountain flow, has proven exceptionally difficult. The models seem to miss key hydrodynamic processes, particularly how efficiently the hot, outflowing wind can mix with cooler halo gas, shed its energy, and cool down enough to turn around and fall back. This recycling rate is not a minor detail. It is a fundamental governor of a galaxy's growth and chemical evolution. If a galaxy cannot reclaim its expelled gas, it will eventually starve, its potential for new stars limited. If it recycles too efficiently, it might not expel enough heavy elements, altering the metallicity of its stars in ways that contradict what we observe. The fact that real galaxies like NGC 253 master this balancing act so seamlessly suggests there is a hidden layer of physics in these gaseous halos, a subtle interplay of turbulence, cooling, and gravity that we have yet to code into our virtual universes. How do galaxies manage to catch their own breath, turning a destructive wind into a life-giving rain? This intricate dance between visible matter and invisible forces leads us to a final, profound contradiction, one that pits the map of dark matter against the light of the stars it supposedly governs. The hidden heart of a dwarf galaxy is not always the same. We find these small stellar systems seemingly similar in their total starlight, yet they spin in ways that tell completely different stories about their dark souls. One dwarf might reveal a rotation curve that climbs steadily toward its edge, another remains stubbornly flat, while a third might even show a peculiar dip or wiggle. This is the paradox of the diverse dwarf rotation curves, a challenge to the idea of a one-size-fits-all dark matter halo. Astronomer Dr. Mario Matteo's work reveals this startling lack of uniformity. If dark matter halos were simple, predictable structures that formed through gravity alone, we would expect a much tighter family resemblance among these small galaxies. The wild variations we actually observe suggest something else is at work. The visible, baryonic matter is leaving its mark on the invisible. A galaxy that experienced a particularly violent burst of star formation in its youth, with supernova churning its core, might have its dark matter pushed outward, creating a flatter, more spread-out distribution. In contrast, a dwarf that formed its stars more gently and quietly could retain the classic, dense concentration of dark matter at its center. A past merger or a close gravitational encounter could further stir this dark pot, scattering and rearranging the halo in a unique way. This diversity means that the final rotation curve of a dwarf galaxy is not just a readout of its initial dark matter endowment. It is a living record, a fossil of its entire life history of stellar births, deaths, and interactions. The dark matter, it seems, is not a rigid scaffold, but a responsive medium sculpted by the very galaxy it is meant to support. Why do these smallest galaxies refuse to follow a single, simple rule? Their individualistic spins are a testament to the profound and complex dialogue between light and shadow, a conversation that writes a unique destiny for every single galaxy in the sky. This intricate relationship between a galaxy's history and its composition extends beyond its rotation, reaching into the very chemical essence of its stars. Even the faintest galaxies refuse to be chemically simple. We would expect the smallest, most fragile dwarf galaxies to be pristine relics of the early cosmos, composed almost entirely of the original hydrogen and helium forged in the Big Bang. Their weak gravity should have made it nearly impossible for them to retain the heavy elements cast out by supernova, leading to a clear trend where the tiniest galaxies are also the most metal-poor. Yet when we measure the chemical makeup of ultra-faint dwarfs like Segway 1, we find they do not follow this rule to its logical conclusion. Instead, they hit a flaw, a minimum level of metallicity that even the most diminutive galaxies seem to possess. This is the metallicity flaw paradox, a chemical puzzle that challenges our story of how the first elements were spread throughout the cosmos. Astronomer Dr. Josh Simon explores the origins of this unexpected baseline. One compelling idea points to the very first generation of stars, known as population 3 stars. These primordial giants, thought to be hundreds of times more massive than our Sun, would have lived fast and died violent deaths, seeding the surrounding cosmic gas with a foundational layer of metals before many of the smallest dwarf galaxies even finished forming. In this scenario, a galaxy like Segway 1 did not have to forge all of its own heavy elements. It formed from gas that was pre-enriched by these stellar pioneers. Another possibility involves external accretion, where a dwarf galaxy slowly siphons off already enriched gas from a passing filament of the cosmic web or from a neighboring system, receiving a chemical inheritance from beyond its borders. Both of these pathways suggest that no galaxy, no matter how small, is truly an island. Its chemical identity is shaped not just by its internal fires, but by the enriched environment it was born into or the gentle flows it has absorbed over eons. This existence of a metallicity flaw forces a profound shift in how we view galactic infancy. It implies that the products of the first stellar deaths were mixed throughout the cosmos with surprising speed and efficiency, ensuring that even the most humble galactic beginnings started with a basic set of elemental building blocks. How this early enrichment occurred so uniformly remains an active mystery, one that connects the intimate chemical fingerprint of a single dwarf galaxy to the grand, cluster-scale architecture of the universe itself. A galactic collision on the most epic scale offers the most direct proof of dark matter's reality, yet simultaneously reveals its deepest mysteries. This is the paradox of the Bullet Cluster, a system of two massive galaxy clusters that have violently passed through one another. The event, studied in detail by astronomers like Dr. Douglas Clow, acts as a natural laboratory for the properties of dark matter. As the clusters collided, the hot, X-ray emitting gas of both systems, which constitutes the bulk of their normal matter, slammed together and slowed down due to its own electromagnetic interactions, like two clouds of smoke merging. The individual galaxies, and more importantly, the invisible dark matter, did not. They continued racing ahead unimpeded. We know this because the dark matter, which cannot be seen, revealed its presence and location through its gravitational lensing effect, bending the light from background galaxies. The result is a stunning separation. The dark matter, mapped through gravity, leads the way while the visible matter lags behind. This observation powerfully confirms that dark matter is real and, crucially, that it is largely collisionless, passing through itself and normal matter with barely a whisper of interaction. Yet the precise details of this separation, the exact offset and the smooth distribution of the dark matter halos, are not perfectly reproduced in our most sophisticated computer simulations. The models struggle to match the fine-grained structure we observe. This subtle mismatch is a critical test for the specific properties of dark matter particles, particularly their potential for self-interaction. The data from the Bullet Cluster suggests that if dark matter particles do interact with one another, their cross-section, the effective area for collision, must be vanishingly small. Even a tiny deviation from perfect collisionless behavior would alter the distribution we see. The fact that our simulations do not perfectly capture this cosmic event tells us that our assumptions about the initial conditions or the fundamental nature of the dark matter particle itself may require refinement. How does this mysterious substance, which makes up most of the mass in the universe, behave when subjected to the most violent gravitational forces imaginable? The Bullet Cluster provides a clear answer, but also a nuanced question, proving the existence of the invisible while reminding us that its true character remains just out of focus. This grand collision of entire clusters forces us to look at the opposite end of the scale, to the delicate and fundamental rules that govern how individual stars are born within a single galaxy. The universe has a rule for building stars, a simple recipe written in the language of gas density. We believed that when a cloud of hydrogen reaches a certain critical threshold, gravity must inevitably take over, collapsing it into brilliant new suns. Yet this elegant rule is being broken right before our eyes. In galaxies like the Large Magellanic Cloud, we find delicate, glowing pockets of stellar birth flourishing in regions of gas so diffuse they should be sterile, regions lying far below our theoretical density limit. This is the paradox of the star formation threshold variation, and it reveals that our simple recipe is missing some vital ingredients. Why does star formation ignite so freely where our models say it should not? Astronomer Dr. Bruce Elmergreen has demonstrated that the threshold is not a universal constant, but a value that shifts and changes depending on the local environment. In a quiet, stable galaxy, the rule might hold, but introduce turbulence and everything changes. Imagine trying to light a candle in a still room versus in a hurricane. Chaotic motions within the gas can create temporary, high-density pockets even within an otherwise thin cloud, providing the extra push needed for collapse. Magnetic fields add another layer of complexity, providing a subtle scaffolding that can either support a cloud against gravity or, if the fields become twisted and compressed, trigger its sudden downfall. Even the harsh radiation from nearby young stars plays a role, potentially compressing distant gas clouds and nudging them over the edge into star formation. Our most sophisticated simulations, however, often rely on a fixed, universal density threshold for simplicity. This computational shortcut leads to significant inaccuracies, causing the models to underpredict star formation in some environments and overpredict it in others, ultimately skewing our virtual timelines of galactic evolution. The reality is that star formation is not a simple on-off switch governed by a single number. It is a deeply local and nuanced process, a delicate dance between gravity and a host of other competing forces. If the birth of stars defies our prescribed rules in the galactic disk, what does that imply for the vast, silent reservoirs of gas that exist far beyond a galaxy's bright edge? The heart of a galaxy cluster should be a cosmic furnace, radiating away its energy and cooling into a river of new stars. These are the cool cores, where the dense, X-ray bright gas at the center was expected to lose its heat through radiation, collapse under its own weight, and fuel a tremendous burst of star formation, a process astronomers call a cooling flow. Yet when we look at massive clusters like the Perseus cluster, this expected river of cooling gas has been stopped by an invisible dam. The core remains searingly hot, defying the fundamental laws of thermodynamics. This is the cool core galaxy cluster problem, a paradox where the universe's largest structures actively resist their own cooling. How does a cluster prevent its central gas from fulfilling its apparent destiny? The leading suspect is a colossal engine at the very center, the supermassive black hole of the central galaxy. Astronomer Dr. Brian McNamara's work points to active galactic nucleus, or AN, feedback as the primary heating mechanism. In this cosmic balancing act, as gas begins to cool and flow inward, some of it feeds the central black hole, igniting incredibly powerful jets that blast back into the surrounding cluster atmosphere. These jets create vast, buoyant bubbles of ultra-hot plasma that rise through the core, churning the gas and reheating it in a process that resembles a gargantuan convection oven. This AGN feedback appears to be a remarkably precise thermostat, preventing the core from either freezing into a starburst or overheating into a void. However, the exact mechanics of this energy transfer remain elusive. Our most detailed simulations still struggle to replicate the subtle, observed temperature profiles of these cluster cores. They cannot quite capture how the energy from the jets is dissipated so evenly throughout the gas, maintaining a stable equilibrium for billions of years. Other processes like mergers or turbulence from galactic motions might also contribute to the heating, but the AGN remains the prime suspect. This paradox reveals a universe governed by self-regulation on the most immense scales, where the most destructive objects in existence, supermassive black holes, act as the careful guardians of their galactic cities, controlling the very climate of intergalactic space. The fact that this balance is so widespread and so finely tuned suggests a profound connection between the life of a single galaxy and the fate of the entire cluster it anchors. These 25 paradoxes are not a collection of isolated failures, but a chorus of clues, each one pointing toward a deeper, more complex reality. They tell us that our cosmic rulebook, while powerful, is still a first draft. The quiet halos missing their satellites, the galaxies spinning without their dark matter, the ancient giants defying time, and the searing hearts of clusters that refuse to cool, all whisper the same truth. Our universe is far stranger, far more inventive, and far more beautifully intricate than our best models have yet been able to capture. The first clues emerged not from the void of space, but from the painstaking measurement of starlight. Astronomer Vera Rubin, charting the rotation of the Andromeda Galaxy, uncovered a truth that would quietly dismantle our cosmic understanding. The stars at the outer edges were not moving slower, as Newtonian physics demanded. They raced at the same speed as those near the brilliant core. This simple, stubborn observation, the flat rotation curve, was the initial crack in the foundation. It could not be explained by the gravity of the stars we could see. The only logical conclusion was the presence of something unseen, a vast halo of dark matter whose gravitational pull orchestrated the galaxy's spin. This was not the end of the story, but the beginning of a deeper mystery. Each time we think we have a handle on the universe, it presents us with a new set of riddles. The shift from a static Newtonian cosmos to Einstein's expanding, relativistic universe was one such revolution, driven by data that refused to fit the old models. Our view of galaxies themselves evolved from isolated island universes to a dynamic web of hierarchical clustering, all because observations forced our hand. The 25 paradoxes we see today are the direct descendants of Vera Rubin's work. They are not signs that science is broken, but proof that it is working exactly as it should. Confronting the gap between theory and observation is the engine of discovery. It is what propelled us from simple telescopes to the profound insights of the Hubble Space Telescope and the upcoming Nancy Grace Roman Space Telescope. It drives the creation of ever more sophisticated supercomputer simulations, virtual universes where we can test our wildest ideas. The great cosmological leaps have always been born from this tension. How will the puzzles of today reshape the science of tomorrow? They are not dead ends, but signposts pointing toward a deeper, more wondrous reality waiting to be uncovered. These 25 paradoxes, from the missing satellites and cusp core problems to galaxies devoid of dark matter and unexpected magnetic fields, form a constellation of anomalies. Each one is a crack in the foundation of our current cosmology, a place where the universe refuses to follow the elegant rules we wrote for it. They tell us, in a chorus of conflicting data, that our understanding of dark matter, the laws of gravity, and the complex dance of ordinary matter is fundamentally incomplete. The path forward demands new physics, whether that means redefining the properties of dark matter, revising our theory of gravity on cosmic scales, or finally unraveling the full power of baryonic processes we have underestimated. This is not a failure of science, but its greatest calling. The next generation of observatories, like the James Webb Space Telescope and the Vera Rubin Observatory, are our gateways to testing the emerging theories that will one day solve these puzzles. They are the tools that will help us write the next chapter of our cosmic story. The astronomer Carl Sagan once reminded us that somewhere, something incredible is waiting to be known. These 25 paradoxical features are the map to that incredible something. They are an invitation to stay curious, to look up at the night sky with wonder, and to support the scientific exploration that pushes the boundaries of human knowledge. Which of these cosmic paradoxes intrigues you the most? Share your thoughts below, subscribe for more deep dives into the universe's greatest mysteries, and join us as we continue to explore the unknown.